Hey pre-calc, hope you're doing well. Today we are going to talk about geometric series, which means that we are adding the terms of a geometric sequence. That is the definition of a geometric series, the sum of a geometric sequence. And if you recall a geometric sequence, its terms are being multiplied by a common ratio, multiplying to get from one term to the next. So to find the sum of a geometric series, we have a nice formula. And I always hate giving you formulas without looking at where they come from. We have two formulas we're going to examine today, but I'm going to do that in a separate video. So do take the time to watch that too, to find those derivations. It really just solidifies those formulas and gives you a bit more foundation with which to use them. So I'd encourage you to watch that when you've finished this. But if we take and add the terms of a geometric sequence, the formula we're going to use is S sub n is equal to a sub 1. That's the first term. This would be the sum of the first n terms. Here's the first term. We're going to multiply by 1 minus r to the n all over 1 minus r. There are a lot of variables in there, so let's just make sure we know what they are. N, anywhere you see n, that is the number of terms. A sub 1, of course, is the first term, and r is the common ratio. So different from the sum of an arithmetic series where you had to know the first term and the last term, this is rather nice. You only need to know the first term and then that multiplying factor, that common ratio. So let's try a few examples and see if we can put this formula to work. Let's look at number 1 here. Let's just make sure it's geometric because this formula only works with a geometric series. Are we in fact multiplying by the same amount? Well, we are. What are we multiplying by? That ratio is 5, multiplying by 5 each time. The other piece we need to know in here is that first term. Our first term is 2. And then we have to know how many terms we're adding together. We can see that here. We're looking for S sub 9. So n is equal to 9. Those are the pieces we're going to use. Let's plug them in. S sub 9 would be the first term of 2 times 1 minus that ratio 5 raised to the n power, n is 9, all over 1 minus that ratio of 5. Now you might look at this and go, ooh, that denominator is going to be negative. How can that be a negative sum? But notice also up here, this also will be negative. So those negatives will cancel out. And I would put that whole thing in your calculator. Do make sure you put that numerator in parentheses. 2 times 1 minus 5 raised to the 9th. There's the numerator divided by 1 minus 5. And it should be reasonable. We're adding fairly large numbers here. I should get a fairly large number. If I get 1 3/7, that doesn't make sense. But 976,562 is a large number, but actually is reasonable and is in fact the sum in this case. All right. It's a pretty nice, straightforward formula. Sure beats writing out all of the terms and adding them up, though we could if we were wanting to check. All right, let's see about number 3 here. We'll do the same thing. We will identify the ratio, the first term, and then we need to find how many terms. So our ratio looks like we're multiplying by 2. our first term is -4, but it's not directly clear how many terms we have. We have to get to -16,384. So we've got some work to do to figure out which term this is and how many terms we are adding. And so I'm going to go back to that formula that for a geometric sequence, that a sub n is equal to that first term times the ratio to the n-1 power. And I can plug in my ratio and my term value and solve for n. So I know a sub n is -16,384. My first term is -4. The ratio is 2. And I'm going to raise that to the n-1. Now I'm just going to solve for n. Divide both sides by -4. That's 4,096. I'd use a calculator for that. Now here I've got a choice. I can recognize that this is a power of 2, or I could use logs to solve this equation. I could change it into log form. I could take the natural log of both sides. 4,096, though, is in fact 2 to the 12th. So by that examination, n must be 13. So that was preliminary work just to find out that I'm dealing with the 13th term here. So now I'm going to use my summation formula to find the sum of the first 13. That would be my first term, -4, times 1 minus the ratio to the 13th power, all over 1 minus that ratio of 2. And if I plug that whole piece into my calculator, I find that I get -32,764. I do just want to stop and make sure that that makes sense. I am adding a whole lot of negatives, so that does make sense that I would end up with a negative sum. All right. Now let's take a look at number 5 with our sigma notation here. Can we do the same thing? This is the explicit formula of this form here. So I can see that a sub 1 would be, if I plugged in my 1, it's going to be 3. My ratio is that base of -4. And how many terms am I adding? I'm going from 1 to 7. So there are 7 terms. So that series right there would be equal to 3 times 1 minus -4 raised to the 7th, all over 1 minus the ratio of -4. So notice I'm adding in the denominator. If I throw all of that into my calculator with correct parentheses in order of operations, I get 9,831. All right, putting that geometric series formula to work. All right, let's look at the second page. I want to look at number 9, because in number 9, notice we go from C equals 2 to 13. So I have to be careful. I don't want to take 7 as my first term, because my sequence, and really the series, begins with a first term when C is 2. So if I want to find that first term, I'm plugging 2 in there. Well, that would be 7 times 3 to the 2 minus 1. That would be 21. So my first term is 21. So this whole series, first term times 1 minus the ratio is 3. And how many terms are there? Remember, we talked about this actually in class on Monday. 13 minus 2 is 11, but that was the spaces between the numbers. I need the endpoint as well. So there are 12 terms. Want to make sure that we get the number of terms correctly and 1 minus the ratio. And again, just a little practice throwing that into your calculator, and you will find that 12 terms add very quickly to 5,580,120. All right. Let's see if we can look at an application. I want to look down here at number 13. Carol wants to be a millionaire. Well, of course she does. If she saves 1 cent on the first day, 2 cents on the second day, 4 cents on the third day, and so on, how many days will it take her to save $1 million? This is a variation on a very classic Algebra 1, Algebra 2 type question when we introduce exponentials. Ooh, I'm hearing music in the background because Mr. Mac turned on his music. So we'll see if he remembers that I'm filming a video. So we want to find out when our sum is $1 million. And so we're really looking for an n value. We're going to use, I'm going to put over here, S sub n is, just to remind myself what this formula is, over 1 minus r. So we really are looking for, where is the sum $1 million? And on the first day, we saved 1 cent. So that's 0.01. And then we have 1 minus our ratio. Well, if you noticed, it was doubling every day. We're looking for n. So the ratio 2 to the n, all over 1 minus 2. Well, 1 minus 2 is -1. So if I multiply both sides by -1 to get rid of that denominator, I have -1 million is equal to 0.01 times 1 minus 2 to the n. Now I'll divide by 0.01, so that becomes -100 million equals 1 minus 2 to the n. Subtract 1, so -100 million, and 1 is -2 to the n. Now notice it's the opposite of 2 to the n. So it's not -2, the quantity raised to the n, so I can just make both sides positive, multiply both sides by -1, or divide both sides by -1, and we have 100 million 1 is equal to 2 to the n. Well, 100 million 1 is not a power of 2, so I've got to use logs in this case. You could take the natural log of both sides, use some log properties. You could take the log base 10 of both sides, use some log properties. But I think I'm just going to change forms and call this log base 2 of 100 million 1. And that would be equal to the exponent of n. And I'm going to grab my calculator for this one. I could use my change of base formula if I wanted to do log of 100 million 1 divided by log of 2. Or remember, if you go into math, I think it's down here. Yep, there it is. On A is log base. This only works if you have an 84, I believe. I don't think any of the 83s have this option, but we can put in a base of 2. And then 100, 1, 2, 3, 4, 5. Make sure you get the correct number of zeros in there. And n is 26.575. So how many days will it take for her to save $1 million? It will be 27 days. 26 days would be too little. You have to move to that 27th day. So, nice reminder of logs in there. Those always come in handy. All right. That is how we handle the sum of a finite geometric series. But what about infinite series? We want to do a little exploration here. Here, if we have the series 1/2 plus 1/4 plus 1/8 plus 1/16, notice that the ratio is 1/2. We're adding half as much each time. And so if I add just the first term, that's a half. If I add the first two terms, notice my common denominator would be that second term. So that would be 3/4. And then the first three terms, these two add to 3/4, but then I need to change them to eighths. So that would be 6/8 plus 1/8 is 7/8. And then if I add the first four terms, I need them all to be in 16ths. This would be 14/16 plus 1 is 15/16. Do you see the pattern here? 1/2, 3/4, 7/8, 15/16. The first five terms, that fifth term would be 1/32. So the sum would be 31/32. And then the sixth term, that would be in terms of 64ths. That would be 63/64, and so on. That numerator is always one less than the denominator, which means that as I add more and more and more and more and more terms, I am really just getting closer and closer and closer and closer to 1. S sub n is approaching an actual value. So I can actually find the sum of this series. The sum is 1 as n goes to infinity. It's a limit right there. And when an infinite geometric series actually goes towards a specific value, we say that it converges, and it is a convergent series. This will happen when the ratio is less than 1. Because if it were bigger than 1, we'd be adding more and more and more and more. And it would approach infinity. It would just grow forever larger. But if the ratio is less than 1, we will actually have a limit on that sum. It won't always be 1. It could be 5. But it will approach a number and it will converge. And that occurs when our ratio is less than 1. But our ratio could actually be negative 1/2 as well, and we would still converge. So we say the absolute value of that ratio needs to be less than 1. If that is true, then this series is convergent or converges. If, however, take a look over here, you can see that each time we move to the next term, we're doubling. Our ratio is 2 here. Look what happens to the sum I get. I'll do these as decimals. 0.5. The first two is 1.5. Then add 2, we get 3.5. Add 4, we get 7.5. Add 8, we get 15.5. Next would be adding 16. We get 31.5. These sums are getting larger and larger and larger because the ratio is larger than 1. Those numbers are getting larger. And so we have what we call a divergent series. The sum approaches infinity. Or it could be negative infinity if our ratio was negative. So if the absolute value of r, the ratio, is greater than 1, this series diverges, or we say it's divergent. Not just a great young adult novel, but mathematically important. It's divergent. It was a good movie too. All right, so if the series diverges, the sum is either infinity or negative infinity. It is not an exact value. But if the ratio is less than 1, so if it converges and is an infinite geometric series, so this only works if the ratio is less than 1 and it's an infinite geometric series, we are going to use this formula. S sub n is equal to the first term over 1 minus r. Now, again, refer to my other video, and we'll talk about where this formula comes from. All right, we're just going to try a few examples. Let's take a look at number 13. We want to determine if the series is convergent or divergent. If it's convergent, we're going to find the sum. If it's divergent, there is not an exact sum, so there's nothing to find. Let's see, we are multiplying. Let's find the ratio. Let's see, we're multiplying, it looks here, by -6. Well, -6, the absolute value of that is greater than 1. So this series, is divergent. Nothing left to do. All right. And in fact, this alternates back and forth. It doesn't have a sum at all. All right. Let's look at number 15. What is the ratio? Well, it looks like we're going by halves and it's alternating, goes negative, positive, negative, positive. So that ratio must be -1/2. Well, that absolute value is definitely less than 1. So this series converges. We have a convergent geometric series, which means that we should be able to find the exact sum according to this formula here. So let's find the sum. S sub n will be the first term, -180, over 1 minus the ratio, and the ratio is -1/2. So that's like negative, or 1 adding a half. And use my calculator for this. -180 divided by 1.5, that is -120. If you wrote all of those out, if that were possible, and added them all together, the sum would be exactly -120. That is really an awesome thing to consider, that we can take infinitely many terms and know what they add to. Take a moment to ponder that. That really is remarkable that we could know the exact sum of infinitely many. If we just did the first 50, we would be approaching it, but there is actually a sum of all of those. All right, look here, we're going from 1 to infinity, so we are looking for the infinite geometric series. What is that ratio? Well, here's the first term. Here's the ratio is 3/4. That is less than 1. So we do, in fact, have a convergent series that we can find the sum of. So S sub n is equal to that first term of 224 divided by 1 minus the ratio of 3/4. And so that's really going to be 224 divided by 1/4. That's like multiplying by 4. So that will be 896. And again, we should just be appreciative and a little in awe of the fact that we can find an exact number for that, for infinitely many terms being added together. Only in a geometric series, though. Does not work in other types of series. And this last one, let's look here. We do have from p equals 1 to infinity, so it's infinite. The ratio, however, is -7/6. The absolute value of -7/6 is 7/6. and that is larger than 1. So this actually is divergent, and there is no exact sum. So there are some key details to keep in mind. Are you looking for an infinite geometric series or a finite geometric series? Determines which formula you use. And in an infinite geometric series, stop and determine, is it divergent or convergent, to determine if it does in fact have a sum. All right, give the homework a try. Also take a look at the other video to learn a little bit more about where those formulas come from. See you next time.